Hello, everyone. My name is Monika Misztela, and I'm a PhD student at the Research School of Earth Sciences at ANU in Canberra. And today I will shortly talk about QEMSCAN, platinum group element geochemistry, and sulfide saturation. And all of this on the example of Mount Hagen in Papua-New Guinea. So the hypothesis of my research is that the sulfide saturation plays one of the most important roles in porphyry systems fertility, and it also can determine the type of the ore in the deposit. So during the early stages of magma evolutions, metals behave as incompatible elements, and they are concentrated in the melt during fractional crystallization. If sulfide saturation occurs early in the system, chalcophile elements would be trapped in sulfide phases and locked up in the magma chamber. So they will not be able to enter the fluid phase and form an economic deposit. However, if sulfide saturation occurs later, after or shortly before volatile saturation, metals may still be able to enter fluid phase and form a deposit. So to find the timing of sulfide saturation, I am actually using the geochemistry of PGEs. And mostly because of their high partitioning into sulfides, which makes them very sensitive indicators of sulfide saturation, they are also easily affected by changes in the system, and their solubility in hydrothermal fluids is low. So it means that they are less mobile than copper and gold, and their concentration in rocks reflects magmatic rather than hydrothermal processes. And to measure the concentrations in rocks, I am using fire assay isotope dilution method, which means that I mix each sample with borax, some sulfur, nickel, spikes, and then all of them I'm placing in the furnace for 30 minutes. And after cooling down, I collect the metal bead, which then is going to be dissolved. Then the solution will be further filtered, dissolved again, and then this solution would be analyzed on the ICP-MS. So another method that I used for the study was QEMSCAN, which can provide different information, such as high-resolution maps and images of mineral and elemental distributions, porosity structure maps, density of samples, but also it can generate quantitative reports. So a few words about Mount Hagen. So Mount Hagen is a mid-Pleistocene stratovolcano located in Western Highlands in Papua-New Guinea, and it was formed somewhere between 420 and 220,000 years ago. It is now extinct, and the last eruption was recorded over 50,000 years ago. And it was selected for my study because of its location and proximity to other deposits, the potassium-rich rocks, which may indicate the potential to host porphyry deposits, but also it was related to a subduction zone. So 13 samples were selected for a detailed petrological description and mineral quantification by QEMSCAN. I used the step size of 15 microns, which is not ideal for the accessory phases, such as spinols and sulfides. And in this study, they were usually smaller than 10 microns. However, it is more than enough to cover major phases with great precision. So what we can see that all the samples exhibit moderately to high porphyritic texture. And in the most mafic samples, we can observe olivine phenocrysts up to 3.5 millimeters. They often coexist with chromites. And also we can see some clinopyroxenes up to 2.5 millimeter, often presenting oscillatory zoning. Intermediate samples also show some phenocrysts of clinopyroxene and olivine. However, olivines are significantly smaller. Also, some sector zoning in clinopyroxenes. So hornblende becomes abundant at about 6% of magnesium content of the whole rock. Plagioclase and potassium feldspar were present in all the samples, and their abundance just changes a little with the fractionation. So for each sample, I also generated a quantitative report for mineral phases, and then it was plotted on the cumulative abundance of major mineral phases versus the whole rock magnesium content. And it is easy now that something had happened at about 6% of magnesium content, and that indicated to me that most probably it was another magma pulse to the system. And the magma must have been wetter than the original one, bringing a fair amount of hornblende with it. But to confirm that theory, I actually checked olivines and the cores as well. And the composition of the olivine cores, we can see that it gradually drops from about forsterite 83 to 52, except for that sample, when again it comes back to about 80. And a reversal of the olivine composition also suggests a new magma influx to the system. Looking at the iron and some trace element patterns, we can see a few things. First, that iron, titanium, and vanadium, they all exhibit a very similar trend, similar to copper as well, which firstly increases up to 8% of magnesium and then decreases. So that was interpreted to be the onset of the magnetite saturation. And the breakpoint in copper trend occurring at about the same time is marking the sulfide saturation. So the correlation between these two processes have been reported previously, and they show that the magnetite saturation lowers the oxygen fugacity of the silicate melt, and it converts soluble sulfides into less soluble sulfides. Taking a look at the PGEs, we can see two distinctive trends that can be observed after the first analysis, which here is in orange and blue circles. And the first trend, despite the scatter, show it's decreasing up to about 5.5% of magnesium when there is a reversal followed by a second decline. So that was interpreted to be a new magma pulse to the system, which is consistent with the previous assumption. But taking a look at the palladium, platinum, and gold, we can also see scatter, which I will address in a moment. But besides that, we can also see that the concentrations initially increase up to 8.5% of magnesium, followed by a decrease up to 5.5, which correlates with the copper trend. So the sulfide saturation occurred at about 8.5% of magnesium. And if that was true, we would expect to see agreement between duplicates prior to that moment because there were no sulfide nuggets. However, as we can see, there is some scattering and there is some disagreement prior to that moment, telling us that the micro nuggets were present in all of the samples. So the simplest explanation to that is that the magma left a sulfide saturated mantle, and that droplets of sulfide melt were carried to the surface as inclusions in phenocrysts. And the sulfides affected the PGEs, but did not affect copper because of its high partition coefficient. So later the fractionation continued until magma reached sulfide saturation at about 8.5% of magnesium content, which led to a sharp decline in palladium, platinum, and gold, and copper as well. So the mixing trend here in gray does not correlate well with the theory that it was mixed with the mafic magma. It shows that it's not possible to produce concentration of these elements simply by mixing fractionated magma with the primitive one. So this gives me an idea that the new magma pools had to come from a different part of the mantle with different initial concentrations of these elements. So PGEs were also used to model the fractionation of palladium, gold, and copper. And it shows that the magma had reached a very early sulfide saturation. And as a result, chalcophile elements would be trapped in the mantle and they would not be able to enter a fluid phase and form a deposit. The three most felsic samples were plotted on the diagram proposed by Park and to distinguish barren copper-only gold-copper deposits. And as all three samples plot on the copper-only area, we have to remember that this new magma pulse was much wetter, higher concentration of platinum, palladium, and gold. And this second pulse of magma could have a potential to form a deposit. However, as we know, just to conclude, we know that Mount Hagen was an open system with at least one major magma recharge. it underwent early sulfide saturation, which makes it unlikely that this type of magma had produced any type of mineralization. So PGEs can be used to identify the onset of sulfide saturation, and it very often correlates with the close timing of magnetite saturation. Thank you very much.